Right now, far out in space, there are objects so strange that big and small stop making sense. Some of them weigh as much as millions of suns, yet could fit inside a space smaller than our solar system. Others are so large that light itself can't escape their edges. We call these objects black holes. Most of us imagine black holes as giant monsters in space. But that picture is wrong, because in the universe, size doesn't work the way it does on Earth. Tonight, we're not guessing. We're using real measurements. Stars we've watched move for decades, distances we can calculate with incredible precision. And by the end of this video, you'll understand how scientists compare things the mind can't picture, and why the true scale of black holes changes how we see the universe. If you're ready to go deeper into this mystery, hit that subscribe button, and together, let's drift into space. There's a moment in astronomy where the numbers stop feeling like numbers, not because they're complicated, but because they're too clean. 1 million, 1 billion, 1 trillion. We can say those words in a single breath, and our brains nod like they understand. But they don't, because our minds weren't built for cosmic scale. They were built for berries on a branch, for footsteps to the river, for the distance to the next hill before night falls. And then, we point that same fragile intuition at the most extreme objects in the universe. Black holes, objects so dense that light itself can't climb out. And suddenly, our normal sense of big and small doesn't just fail, it fractures. Here's the uncomfortable mystery we're stepping into. If we can't truly imagine the scale of a black hole, how do we ever hope to understand what it is? Let's be honest about what we are. We are a species that thinks in human distances, a room, a street, a city. We're good at survival scale math, but cosmic scale doesn't increase like a staircase, it increases like a cliff. A few steps out from Earth and the moon becomes a speck. A few steps farther and Earth becomes a pale dot. A few steps farther and the sun becomes one star among hundreds of billions. This is why astronomers rarely speak in raw distance alone. They build bridges for the mind, because when scale becomes too large, the brain does something dangerous. It stops feeling the difference. 1 million and 1 billion both become a lot. 1,000 and 1 million both become huge. And that is exactly how the universe hides its true proportions from us. We can count, but we can't feel counting past a certain point. Most of us can picture 10 objects without strain. We can picture 100 with effort. But after that, it becomes fog. We start using labels instead of understanding. Massive, enormous, unfathomable. And words like that are comfortable. They let us stop. But black holes don't allow that comfort, because black holes are not just big. They are a test of whether we can hold two opposing truths at once. A black hole can be small in size and still contain the mass of many suns. That contradiction is where our intuition collapses. Here's the difference that quietly controls everything. Most of our daily thinking is linear. If something doubles, we expect it to feel twice as much. 2 apples, 4 apples, 8 apples, we can follow that. But cosmic scale behaves more like an elevator than a staircase. One step in distance can suddenly swallow entire worlds. One step in mass can suddenly change the rules of physics nearby. Astronomy is filled with these leaps. Earth is about 12,700 kilometers across. The Sun is about 1.4 million kilometers across. The distance from Earth to the Sun is about 150 million kilometers. Just saying those numbers doesn't help, because our minds treat them like the same kind of far, but they aren't. They're different universes of distance, and black holes live at the far end of that elevator shaft. Imagine this. We're standing in a school hallway with a 1-meter ruler. At first, it's perfect. We measure a backpack, a doorway, a classroom. Our tool makes sense. Now we walk outside and try to measure a highway. We can still do it, but it takes time. Then we try to measure a continent. Now the ruler becomes absurd. The tool is the same, but the scale has changed so much that the tool stops being practical. That's what happens inside our minds. Our mental ruler is made for human scale. cosmic scale doesn't just stretch it, cosmic scale makes it meaningless. So, astronomers do something brilliant. They don't rely on our internal ruler, they build external ones. Black holes are the ultimate test because they attack us from two sides: size and mass. With most things, these track together. Bigger object, more stuff inside, more mass. But black holes break that comfort. A black hole's defining feature isn't a surface we can touch. It's a boundary in space, a line where escape stops being possible, and that boundary can be shockingly compact compared to the mass it contains. This is where the story becomes unsettling. Some black holes can be heavier than stars, while being only a few dozen kilometers across at the event horizon. They can be millions of suns, while still being solar system scale, not galaxy scale. They are not just big things, they are extreme concentration, and concentration is what the human brain struggles with most, because we are used to mass being spread out, like sand on a beach, like water in a lake, like air in a room. Black holes are the opposite. They are mass folded inward, packed down, tightened, until reality itself changes its behavior nearby. This is where the story cracks open, because even our language sabotages us. We say whole, and we picture emptiness, but a black hole is not empty. It is an object with mass. We say black, and we picture darkness like paint, but a black hole isn't black because it's coloured. It's black because light can't escape once it passes the boundary. We hear the name and our brain builds the wrong picture, and that wrong picture spreads. It makes us imagine black holes as cosmic mouths, wandering the universe, eating everything. But gravity doesn't work like hunger. A black hole doesn't pull harder because it's spooky. From far away, a black hole's gravity behaves like the gravity of any object with the same mass. This is why the real danger of black holes isn't a simple fear. It's a misunderstanding, and misunderstanding is how scale defeats us. Because scale isn't just how big something is. Scale is how wrong our instincts become when the universe stops behaving like our daily life. Here's the strange part. If we keep thinking bigger means more extreme, we miss what black holes are actually doing. Some of the most extreme black holes are not the biggest ones. They are the ones where a star's mass is compressed into a region the size of a city, or smaller. That's when gravity becomes a trap. That's when time itself starts behaving differently. That's when light bends and the universe stops offering clean, comfortable intuition. And we need to say this slowly, because it's the foundation of everything that comes next. Black holes are not measured by how they look. They are measured by what they do. So how do astronomers keep their footing? They don't just throw numbers into the air and hope we catch them. They build comparisons that map one-to-one with something our minds can hold. They use reference objects, anchors. They use the Earth-Moon distance to make the solar system feel real. They use the Earth-Sun distance, one astronomical unit, to keep planetary scale stable. They use light years not because it's poetic, but because it's practical. Distance becomes time, and time is something we understand in our bones. And when even light years become too big, they step up again. They use star clusters. They use the Milky Way's diameter, about 100,000 light years, as a familiar hallway in the cosmic mansion. They use galaxies, and then clusters, and then the observable universe itself, about 93 billion light years across. Each step is a new ruler. Not because scientists enjoy complicated units, because without these rulers, the universe becomes a blur, and black holes are exactly where the blur becomes lethal to understanding. If you can calmly say a billion, your brain will try to pretend it has done the work. But saying a number isn't the same as holding it. A billion seconds is not a long time. A billion seconds is about 32 years. That's a lifetime of mornings. Now imagine a trillion seconds. That's not a bit longer. That's more than 30,000 years. Older than cities, older than most recorded history. This is the gap we're fighting. The universe doesn't just scale up, it leaps. And our minds if we don't force them to slow down, will collapse everything into the same emotional bucket. Big. Here's what makes this truly disturbing. The universe can be brutally honest and still feel like it's hiding something, because our perception is the weak link. Two black holes can differ in mass by a factor of 10, and we can barely feel the difference. A black hole can be only tens of kilometers across, and contain more mass than anything we've ever known directly. This is why astronomers obsess over scale, not as trivia, as survival. Because if we don't respect the scale, we don't understand the physics. And if we don't understand the physics, we misunderstand what black holes truly are. Not monsters, not myths, but consequences. Consequences of gravity and collapse, played out on scales that break our minds. So what do we do with this? We stop trusting our instincts as the final judge. We treat our intuition like an early draft. Useful, but unreliable. And we adopt the method astronomers have built over centuries. We measure by comparison. We translate by reference. We build ladders for the mind. We accept that small and large are not enough. We replace them with how massive, how concentrated, how does it bend the motion of nearby stars, how does it shape light, how does it change time? Because black holes are not just objects, they are the most extreme demonstration that scale is not decoration. Scale is the story, and if you feel a quiet resistance right now, a feeling like your mind wants to look away, that's not weakness. That's your brain doing what it evolved to do, protect you from useless complexity. But this is not useless, because black holes sit at the boundary between what we can imagine and what we can still measure. They force us to grow up cognitively. They force us to replace comfort with clarity, and once we do, we're ready for the next step. Now we've built the ruler. We've admitted our limits. We've learned how astronomers keep scale from turning into fog. But the universe has one more twist, because the moment we ask, how big is a black hole, we discover the answer depends on which kind we're talking about. Some black holes are small by cosmic standards, born from the catastrophic death of massive stars, and yet these small black holes can be so dense, so compact, so violent in their concentration that our everyday sense of matter doesn't survive the comparison. So next, we descend into the first true category of black holes we can measure in our own galaxy, the smallest black holes we know exist. And once we see their scale, we'll understand why the word small is about to lose its meaning. When we hear the words black hole, our minds reach for something enormous, a cosmic mouth, a galaxy eater, a darkness the size of a nebula. But the universe has a quieter way of terrifying us, because the smallest black holes we know exist are not big in the way our instincts expect. Some of them are only a few times heavier than our sun, and yet their point of no return can be measured in kilometers, not light years, not even the width of a continent, kilometers. And that's where the discomfort begins, because if something can hold the mass of a star inside a region the size of a city, what does small even mean anymore? To understand these small black holes, we have to begin with a simple truth. Stars do not die politely. A star lives in balance, gravity pulling inward, heat and pressure pushing outward, for millions, sometimes billions of years. It holds itself up. But then, deep in its core, the fuel runs thin, the pressure weakens, and gravity, patient, absolute, takes over. Massive stars don't just fade away, they collapse. And in that collapse, the universe makes a choice. Sometimes the core becomes a neutron star, a city-sized object made of crushed matter. But if the core is too heavy, if gravity has enough mass to overwhelm every known pressure, then the collapse doesn't stop. It continues, past resistance, past structure, past anything that looks like a surface. And what remains is a black hole, not a hole in the ordinary sense, a region where escape stops being possible, a boundary drawn by gravity. Here's where the story cracks open. Because the formation of a stellar black hole is not just an event, it's a catastrophe of scale, compressed into seconds. The outer layers of the star can explode outward in a supernova, bright enough to outshine an entire galaxy for a brief moment. But at the center, the core is doing the opposite. It's falling inward, not slowly, not carefully, it's collapsing under the weight of its own existence. And this collapse was not always accepted as real. Einstein's equations allowed black holes, but even Einstein doubted nature would actually build them. Later, scientists like J. Robert Oppenheimer and Hartland Snyder described how a massive star's core could collapse beyond escape, and eventually the sky began to confess. X-ray telescopes, NASA's Chandra X-ray Observatory, ES emissions and others revealed systems where a hidden object was feeding, pulling gas off a companion star, heating that gas until it glowed in X-rays, right before vanishing. They couldn't see the black hole, but they could see what it did to matter, and the evidence kept repeating the same message. Some of the smallest black holes are born from the deaths of massive stars. So, how small are we talking? For stellar black holes, astronomers typically measure masses in the range of about 3 to 100 times the mass of our Sun. 3 to 100. That sentence sounds clean, but it hides something disturbing. Even at the low end, just a few suns, this is not a small thing in any human sense. Our Sun alone contains almost all the mass in the solar system. So, 3 suns isn't 3 campfires, it's 3 suns worth of matter, crushed into a region that can be smaller than a city. And at the upper end, tens of suns, approaching 100, we're talking about objects that can form from the most extreme stellar deaths, and sometimes grow through mergers or feeding. So yes, in the universe's hierarchy, these are small, but to us, they are already beyond sanity. Now comes the part that makes our intuition stumble. For black holes, mass and size don't relate the way we expect. For ordinary objects, if we add more mass, the object usually gets larger in an obvious physical way. But a black hole doesn't have a normal surface. Its size is the size of the event horizon, the boundary where escape becomes impossible. And here's a simple way to hold it. For a non-spinning black hole, every sun's worth of mass adds roughly 3 kilometers to the radius of that boundary. So, a black hole with about 3 suns has an event horizon radius on the order of about 9 kilometers. That's not the width of a country, that's the width of a city. And if we scale up to around 100 suns, that boundary grows to around a few hundred kilometers. Still not a planet, not even close. It's closer to the size of a long road trip. This is why black holes are such a brutal test of scale. Because we are forced to say a sentence that feels impossible. A stellar black hole can contain star-scale mass inside a human-scale boundary, and the universe does not blink when it does this. Imagine this. We're watching a skyscraper collapse, an intentional demolition. At first, it looks controlled. A few floors drop, dust rises, the structure folds inward. Now imagine the same collapse, but the building never hits the ground. It keeps collapsing beyond the basement, beyond the foundations, beyond the soil, not because it's falling into a hole, but because gravity refuses to let the collapse stop. In this analogy, the skyscraper is the star's core. The collapse is gravity winning. The moment the collapse becomes unstoppable is the birth of the event horizon. A black hole is what happens when collapse becomes a permanent condition, not a thing that swallows. A boundary that forms because the universe can no longer provide an escape route. Now picture this carefully. If you could drift near one of these stellar black holes still outside the event horizon, you wouldn't see a giant sphere of darkness floating like a planet. You'd see space, you'd see stars, you might even see gas glowing as it spirals inward, heating up, shining in X-rays. And the boundary itself? It would be invisible. But you would feel the wrongness of it in the way the universe behaves, because near that line, the rules begin to tilt, quietly, Not with sound, not with drama, with geometry. Now we arrive at the word that always follows black holes like a shadow: density. Even though black holes don't have a surface like a rock, and density becomes a slippery concept the deeper we go, we can still grasp the core idea. Stellar black holes are unbelievably massive for how small their event horizons are. They represent mass concentration at a level our daily world never shows us. In everyday life, mass is spread out. A mountain spreads across kilometers. A city spreads across neighborhoods. Even a star spreads across 1,000,000 kilometers of glowing gas. But a black hole takes star mass and compresses the outcome into a boundary that can be tens of kilometers. That means the gravitational field near the boundary is extreme, and that extreme gravity doesn't just pull on objects, it reshapes the meaning of distance, time, and escape. This is the doorway into the next chapter of our story, because once we accept small but massive, we're forced into the next contradiction. The bigger the black hole gets, the less dense it can become, on average. That should feel wrong. And yet, it's true. But we're not there yet. First, we need to hold one more uncomfortable truth. Stellar black holes aren't rare curiosities. Astronomers expect our galaxy alone may contain millions of them. Most are quiet, no feeding disk, no bright flare, no dramatic glow, just dark, compact mass moving through the Milky Way like invisible wreckage from ancient stellar deaths. We don't notice them because they don't announce themselves. But their existence changes the story of what a galaxy is, because galaxies are not just stars and light. They are also the remnants, the collapsed cores, the invisible mass left behind by generations of death. And black holes are the most extreme remnants of all. If you hold a globe in your hands, Earth, shrunk down to something you can rotate with your fingers, you feel in control of scale. You feel like the universe is something we can model. But then, we place a stellar black hole beside that mental image, a few suns of mass, with a boundary the size of a city, and suddenly our control disappears, because we realize the universe can compress reality so violently that the word object stops feeling adequate. We are not looking at a big thing, we are looking at a rule change. So now we've learned something foundational. Stellar black holes are born from the collapse of massive stars. Many fall into a typical range of about 3 to 100 suns. Their size is not a surface, it's the event horizon. And for these black holes, that boundary can be measured in tens to hundreds of kilometers, which means even the smallest black holes are still brutally concentrated in mass. And yet, this is only the beginning, because mass concentration is just the doorway. The deeper question is how dense these objects really are, and why the answer behaves in the opposite way we expect. Here's the strange part. If we compare black holes by average density, the universe pulls another trick. Small black holes can be denser than anything we know, but bigger black holes can be less dense than small ones. That should be impossible, but it isn't. And to understand why, we have to step into the next chapter, where we stop talking about big and small and start talking about density in a way that challenges every instinct we have. Because once we calculate it, the numbers won't just surprise us. They'll rewrite what we thought compression even meant. We think we know what density feels like. We've held a rock in our hand, we've lifted a bucket of water, we've watched a ship float because steel can be arranged in a way that traps air. Our instincts learn one simple rule. More mass in the same space feels heavier. More mass squeezed tighter feels denser. But then we step toward black holes, and the universe does something almost cruel. It takes the densest objects we know and whispers a sentence that sounds like a mistake. The biggest black holes can be less dense, on average, than the small ones. That should be impossible, and yet it's written into the geometry of gravity itself. So here's the mystery we're carrying forward. If black holes are the ultimate objects of compression, how can more sometimes mean less? Before we go deeper, we need to be careful with language. A black hole doesn't have a normal surface. It doesn't have a solid shell we can measure with calipers. What it has is a boundary, the event horizon, the edge where escape becomes impossible. So when astronomers talk about black hole density, they usually mean a very specific practical idea: average density. We take the black hole's mass, measured from its gravitational influence, and we compare it to the volume of a sphere whose radius is the event horizon. It's not a claim about what the inside looks like. It's not a map of the interior. It's a way to translate cosmic mass into a human concept. How much mass is associated with a region of space this size? That's the bridge. And now we cross it. Density in our everyday world is simple: mass divided by volume. So astronomers do the same thing here, carefully, using the event horizon as the size. And the moment we do, something unsettling appears. A typical stellar black hole, say about 10 times the mass of the Sun, has an event horizon radius of roughly 30 kilometers. That's not the size of a planet, that's the size of a commute. Now place the mass of 10 suns inside that sphere, again, as an average. The number that comes out is staggering: an average density on the order of 100 trillion grams in every cubic centimeter. That's roughly comparable to the density of an atomic nucleus. Not a little denser than steel, not a lot denser than lead, nuclear scale density. And that's when our intuition starts to fracture. Because we realize something: black holes don't merely contain a lot of mass. They contain it in a way that makes ordinary matter feel like fog. Let's build a ladder our minds can climb. Earth has an average density of about 5.5 grams per cubic centimeter. Rock, iron, oceans compressed into a planet. A neutron star, the crushed core left after a massive star collapses but doesn't become a black hole, reaches densities around 100 trillion to 1 quadrillion grams per cubic centimeter. That range is hard to hold. So we anchor it. A neutron star takes something like the mass of the Sun and compresses it into a sphere about the size of a city. Now compare that to an atomic nucleus, the dense center of an atom, which is also around hundreds of trillions of grams per cubic centimeter. This is the domain where matter is no longer stuff in the ordinary sense. It's pressure, it's quantum rules, it's resistance that feels more like a law than a material. And here's the strange part. When we calculate the average density of a stellar black hole, we land in that same neighborhood. Not because the black hole is made of nuclei, but because the mass associated with its horizon is so violently concentrated that our familiar categories collapse. And still, that's not the whole story. Because the moment we scale the black hole up, the average density falls. Imagine this. We have 100 identical heavy books. We stack them into a tight cube. Dense, compact, hard to move. Now we take the exact same number of books and spread them across a huge shelf system. Same mass, far more space. The density drops, not because the books change, but because the container grew. That's the key. For black holes, the container we use is the event horizon, and as the black hole gains mass, that horizon expands. But it expands in a way that creates a trap for our instincts. Because the horizon doesn't grow like a box getting slightly bigger. It grows like a boundary that keeps pulling away from us. Here's the quiet mathematical truth, spoken in human language. When a non-spinning black hole gets heavier, its event horizon grows in proportion. Twice the mass, roughly twice the horizon radius. But volume doesn't scale that way. If radius doubles, volume grows by 8. So if mass doubles but volume becomes 8 times larger, the average density drops by a factor of 4. That's the whole paradox in one breath. More mass makes the boundary bigger faster than it makes the average density grow. And once we see this, the universe gets even stranger. A supermassive black hole, millions to billions of suns, can have an average density that is no longer nuclear. it can fall into densities that feel familiar, even ridiculous. For example, a black hole around 4 million suns, like the one at the center of our galaxy, has an average density on the order of 1,000 grams per cubic centimeter. That's dense compared to water, yes, but it's not nuclear horror. It's closer to the density of heavy materials, just on a cosmic scale. And if we go bigger, around 100 million suns, the average density can be around a few grams per cubic centimeter, comparable to water. And higher still, around 1 billion suns, average density can drop to tens of kilograms per cubic meter, closer to the density of air than the density of rock. At the highest masses we've measured, the average density can become almost ghost-like. This is not poetry. This is what the scaling implies when we use the horizon as our container. And it creates a deeper discomfort. If a black hole can be less dense than water, why is it still the most inescapable thing we know? If you try to picture less dense than water, your mind reaches for something that floats, foam, mist, a balloon. But we're not talking about something that drifts away in the breeze. We're talking about an object whose gravity can dominate the heart of a galaxy. So our instincts revolt because they're mixing two different ideas: average density inside the horizon, the intensity of gravity near the horizon. A supermassive black hole can have a low average density and still produce an event horizon that nothing crosses back from, because what matters for the horizon is not density like a material. What matters is the relationship between mass and the geometry of space-time. Density is our metaphor, gravity is the law, and now we arrive at the darkest word in this entire subject, the word that people whisper like it explains everything: singularity. When people hear singularity, they often imagine a tiny, ultra-dense ball of matter, a pinpoint, a marble, a bead of infinite weight. But in modern physics, singularity is not a physical object we've observed. It's something more unsettling. It's a sign that our current map breaks. In Einstein's general relativity, if we follow the math inward, past the event horizon, the equations can predict that curvature becomes infinite. That's what singularity means in this context, a place where the theory stops giving finite, meaningful answers. In the 1960s, Roger Penrose and Stephen Hawking developed what are now called singularity theorems, showing that under very general conditions, gravitational collapse in general relativity leads to singularities, more precisely to a breakdown in the paths that define space-time. Not because they liked singularities, but because the theory points there. And this is crucial. A singularity is not a verified thing at the center we can describe like a planet. It's the edge of what general relativity can reliably tell us. Most physicists expect that a complete theory, one that unites gravity with quantum physics, would replace the infinite prediction with something finite and physical. But we do not yet have that tested theory. So singularity is best understood like this: not a destination, a warning label, a reminder that our knowledge has limits, and that black holes drag us directly toward them. Now we can see the full shape of the paradox. Small stellar black holes have extreme average densities, near nuclear scales. Supermassive black holes can have surprisingly low average densities, and yet both create event horizons where escape becomes impossible. So density isn't the simple power meter we want it to be. A black hole's danger, its authority, is not just how much mass is packed. It's how that mass warps space and time into a geometry with no exit. And the most unsettling part is what this implies for us. Black holes are not defined by what they are made of. They are defined by what they do to the structure of reality. If you stand on a beach and scoop a handful of sand, you feel weight. You understand density in your muscles. But if we try to feel the density of a black hole, we can't. We can only translate. We can only build ladders of comparison. Earth, neutron stars, nuclei, and then admit that even those ladders end. Because black holes aren't just heavy, they are where our familiar concepts, volume, interior, material, start to lose their meaning. And that is exactly why scientists hate mysteries. Because here, the mystery isn't in the sky, it's in our tools. So here's what we can say, cleanly, fact first, without mythology. We estimate a black hole's average density by dividing its mass by the volume implied by its event horizon. Stellar black holes can reach average densities comparable to neutron stars and atomic nuclei. As black holes get more massive, their horizons grow and their average density decreases because volume grows faster than mass. The singularity is not a confirmed physical object we've observed. It's the point where general relativity predicts infinities, signaling the limits of the theory. And this leaves us with a sharper, more unsettling question. If the most extreme objects in the universe can have average densities that range from nuclear scale to air-like, then density alone can't be our compass. So how do we actually know these objects are there? How do we measure mass when the object itself is invisible? When the boundary can't be photographed like a mountain? When the interior is sealed behind a horizon we can never cross? Because the universe has one more twist. Black holes don't need to be seen to be measured. They leave fingerprints in motion, in light, in heat, and in the behavior of nearby stars. And that's where we go next, to the methods astronomers use to weigh the invisible with astonishing precision, without ever touching the thing itself. Black holes are not difficult to describe, but they are difficult to catch, because the thing we're hunting doesn't glow, it doesn't reflect, it doesn't give us a surface to photograph. A black hole is defined by a boundary, the event horizon, where escape becomes impossible, even for light. So here is the problem. If the most extreme objects in the universe refuse to show their face, how did we ever become confident they exist at all? Imagine this. You walk into a dark room and someone tells you there's a fan spinning in the corner. You can't see the blades, but the curtains are breathing. Dust is moving in spirals. Your skin feels the air shift. You can't see the fan, yet the room is confessing its presence. That is how we measure black holes. Not by looking at them, but by watching the universe react. And once we learn how astronomers do this, we realize something unsettling. Some of the most precise measurements humans have ever made were made on objects we cannot see. A telescope is a simple contract. It collects light, it turns photons into information, it makes the distant visible, but a black hole breaks that contract. NASA puts it bluntly, because light can't escape, black holes themselves neither emit nor reflect it. Nothing from inside can reach an outside observer. NASA also emphasizes the event horizon is not a solid surface, it's a boundary. So when we point a telescope at a black hole, the black hole doesn't appear as an object. It appears as an absence. An absence is not easy to prove. Scientists hate mysteries that can hide behind, maybe it's just dark. So, astronomy built a different strategy. Instead of searching for light from the black hole, we search for motion, heat and distortion around it. Gravity becomes our ink. The cleanest clue a black hole leaves is simple motion. If an unseen object has mass, it pulls. And if something nearby is moving in a tight, fast orbit, then something heavy is sitting at the center, whether we like it or not. The Chandra X-ray Observatory's Educational Field Guide explains it plainly. We can't see a black hole directly, so we use circumstantial evidence, especially the orbital acceleration of a star around an unseen companion in a binary system. This is the first method that feels almost classical. Kepler wrote the rules for planetary orbits centuries ago. NASA still teaches the same core idea. Orbital period and orbital size are linked in a way that lets us infer the mass of what's being orbited. So when astronomers track a star's orbit and find it is racing around something invisible, they can estimate the mass of the hidden object. And here's where it gets sharp. If that inferred mass is too large to be a neutron star, too heavy to be any stable ball of matter, then one possibility remains: a black hole. But then it gets stranger, because in many systems, the orbit alone isn't enough. You also need the speed toward us and away from us, the part of motion our eyes can't see. That's where the story cracks open into light itself. A black hole may be invisible, but the star beside it is not. When that star moves toward us, its light shifts slightly bluer. When it moves away, the light shifts redder. That shift, measured in spectral lines, is the Doppler effect, the same principle NASA uses to teach orbital motion in our own solar system, just applied with far higher stakes. A simple analogy: 1-to-1, no distraction. It's like listening to an ambulance pass you on the street. As it approaches, the sound feels higher. As it leaves, it drops. Your ears don't see the speed, yet the shift tells you the motion. Astronomers do this with light. They turn starlight into a heartbeat of velocity. They map a hidden orbit in numbers. They infer the mass that must be creating that orbit. And careful researchers also warn, using radial velocity alone can create false positives. Astronomers cross-check with other signals so they don't mistake an ordinary system for a black hole. This is the rhythm of real astronomy. Measure, doubt, verify, tighten the net. But even this isn't the loudest evidence, because sometimes a black hole doesn't just pull on a companion star. Sometimes it feeds. Here's the disturbing part. A black hole doesn't have to emit light to be found. It only needs nearby material, gas, dust, a companion star, something that can be stolen. NASA describes this directly. Some black holes pull material from a companion star. As the material falls in, it heats up and lights up in X-rays. This is not metaphor. This is temperature and gravity. Real heat. Real photons. The material doesn't fall straight in. It spirals, forming an accretion disk, matter grinding around the abyss, heating through friction and compression. A simple physical analogy. It's like metal pressed to a spinning grinder. The grinder itself is dark, but the contact throws off sparks. Those sparks don't tell you the grinder's color. They tell you the forces at the edge. In black holes, those sparks can be X-rays, captured by observatories like NASA's Chandra, and analyzed with the same calm rigor used everywhere else in physics. And then the universe offers an even finer tool: timing. NASA's NICER mission has used light echoes, X-ray reverberation mapping, to probe the geometry close to the event horizon region in black hole systems, watching delays between direct emission and its reflection off the disk. We don't just see brightness, we see structure in time. But this creates a bigger problem, because when the object is invisible, every method is indirect, and indirect measurements can drift into uncertainty, unless we have a system so clean, so well tracked, so brutally precise, that doubt starts to run out of places to hide. This is where modern astronomy becomes almost surgical. When astronomers can track stellar motion with extreme accuracy, positions, velocities, changes over years, they can pin down the mass of the unseen central object with startling precision. The European Southern Observatory describes decades of work tracking stars near the center of our galaxy, with key focus on a star called S2, whose orbit provided some of the strongest evidence for the supermassive black hole there. The Nobel Prize in Physics 2020 recognized this achievement. Reinhard Genzel and Andrea Ghez were honored for showing an invisible, extremely heavy object govern star orbits at the Milky Way's center, where a supermassive black hole is the only currently known explanation. Even the instrumentation tells a story of precision. An institute release about ESO's gravity instrument describes astrometric measurements at the level of tens of micro-arcseconds, a precision so fine it's like resolving a coin on the moon from Earth. And a science paper on the star S02, S2, discusses detecting the relativistic redshift expected as the star passes close to the supermassive black hole, another layer of measurement stacked on top of orbit tracking. This is why black hole mass measurements can be among the most precise in astronomy, because gravity is honest. It can't pretend. It can't disguise its mass once we measure motion carefully enough. And then there's one more kind of seeing, a method that feels like the universe finally letting us peek through the keyhole. The Event Horizon Telescope. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole. The bright ring formed as light bends in intense gravity around the supermassive black hole in M87. JPL's explainer notes the image shows a ring of light around a black hole about 6.5 billion times the Sun's mass. Not a photo of the black hole itself, but a silhouette shaped by extreme gravity. This matters for our theme, measuring the invisible. Even our most iconic image is still indirect. A shadow, a warped glow, a gravitational imprint. And yet, it's real. It's physics made visible. You can stare at that ring and feel the contradiction. The universe gave us a picture, but it's a picture of light being bent around something that refuses to be seen. But that's not the whole story. Because the most intimate black hole we can study isn't in a distant galaxy. It's inside our own. So now we have the toolkit. We track orbits and acceleration to infer hidden mass. We read Doppler shifts to measure motion we can't see directly. We detect X-rays from infalling matter, accretion disks turning gravity into heat and light. And with extreme instruments, we measure star positions so precisely that the mass at the center becomes unavoidable. But this creates a deeper mystery. What happens when we apply all of this to the nearest supermassive black hole of all, the one that doesn't live in a textbook? It lives in our night sky, buried behind dust and starlight, quietly commanding the Milky Way's core. Next, we descend into that crowded, violent region, where stars whip around an unseen center on tight clocks, and where decades of measurement turned a dark idea into a measured object. Sagittarius A star. We keep talking about black holes like they live far away, in distant galaxies, in unreachable darkness. But one of the most important black holes in science is not far in the cosmic sense. It's here, in our own Milky Way, about 26,000 light-years from Earth. Close enough that, for decades, astronomers have watched nearby stars move under its grip in real time. And yet we can't see it. Not because our telescopes are weak, not because we haven't tried, but because the center of our galaxy is a crowded, dust-choked storm, starlight smothered by interstellar debris. Even our best eyes need infrared precision just to look through the haze. You can look up on a clear night and feel it, the Milky Way as a pale scar across the sky, and buried behind that beauty is a gravitational secret, a black hole with the mass of about 4 million suns. And once we truly grasp what that means, our idea of home changes. They call it Sagittarius A star, SGR A star, not a glowing object, a radio source, a gravitational anchor, a place where space bends so deeply that the galaxy's central stars move like iron filings around a hidden magnet. This isn't mythology, it's measurement. NASA and JPL describe Sagittarius A star as the supermassive black hole at our galaxy's center, with a mass around 4 million suns and a distance just over 26,000 light-years. And now we face the contradiction that defines this entire story. If it's that massive, why doesn't it dominate the sky like a second sun? Because mass doesn't need light to rule, it only needs gravity. Here's where the story cracks open. Astronomers didn't find Sagittarius A the way we find a planet. They cornered it, patiently, through decades of watching stars orbit something they couldn't see. Two teams on opposite sides of the world built the case. Andrea Gheze's group used the W.M. Keck Observatory in Hawaii. Reinhard Genzel's group used the European Southern Observatory's telescopes in Chile. Both relied on adaptive optics and infrared imaging to cut through atmospheric blur and galactic dust, and their evidence became so strong that the Nobel Committee called it what it was: an invisible, extremely heavy object governing stellar orbits at the Milky Way's center, where a supermassive black hole is the only currently known explanation. But that's not the whole story, because the most haunting proof wasn't a press release. It was a star. One star, S2, also known as S02, became a kind of cosmic stopwatch. It travels on a long, stretched orbit that takes about 16 years to complete, swinging close to the unseen center, then fleeing back out into the galactic crowd. And in 2018, during its closest pass, S02 came within about 120 astronomical units, roughly 120 times the Earth-Sun distance, and reached speeds around 2.7% of the speed of light. That should be impossible for an ordinary cluster of stars, because a star moving that fast needs one thing at the center: a compact mass, a deep gravitational well, a single dominant object. And the measurements didn't just show fast motion, they showed Einstein's fingerprints. Teams detected the relativistic redshift, light losing energy as it climbs out of the deep gravitational field, right where general relativity says it should. This wasn't a metaphorical agreement, this was a star acting like a test particle in Einstein's space-time. And that creates a deeper mystery. If we can measure relativity itself near the Milky Way's center, what does that say about the black hole's true scale? Imagine this. You're in a dark playground at night, holding a ball on a string. You can't see your hand, but you swing the ball in a circle. The ball draws the shape. The tension in the string tells you the pull. Even in darkness, the motion reveals the hidden center. That's what these stars are doing. They are the visible ball. Sagittarius A star is the unseen hand, and the universe doesn't let them lie. Now, we translate the mass into something we can feel. JPL explains that the distance from the center of Sagittarius A star to its event horizon, its Schwarzschild radius, is about 12 million kilometers, or 0.08 astronomical units. That number is the knife edge of scale, because 0.08 astronomical units is inside the orbit of Mercury. So we're looking at a black hole with the mass of millions of suns, and an event horizon radius that, on a solar system map, fits in the inner neighborhood near our star. And then comes the detail that makes our skin go cold. JPL notes that despite this enormous physical size, Sagittarius A star looks tiny from Earth. Its apparent radius is about 10 microarc seconds, likened to the angular size of a large blueberry on the moon. That's the true insult of distance, a monster at the center of our galaxy, reduced on our sky to something smaller than our imagination can hold. But the measurements still hold, because gravity doesn't care how small something looks. Gravity only cares how much mass is there. And here's the strange part. Sagittarius A star isn't constantly devouring matter like the bright quasars we see across the universe. NASA describes it as close enough that we can witness the flow of matter nearby, including observations of hot gas swirling around it. But overall, it is relatively quiet compared to the most active galactic nuclei. That calmness is deceptive, because quiet doesn't mean weak. It means the beast is resting, and this creates a bigger problem. If our galaxy's central black hole is relatively calm, then what happens in galaxies where the central black hole is actively feeding, pouring radiation and jets into space, reshaping entire star systems? In 2022, the Event Horizon Telescope released the first image of Sagittarius A star, a bright ring surrounding a central darkness, consistent with the expected shadow of a black hole. The image didn't show the black hole as an object. It showed light bending around an absence, a silhouette carved out of radiation. And once again, the universe repeats its theme. We don't see the monster. We see what the monster does to everything near it. We've stepped into the Milky Way's core and watched stars reveal an unseen ruler. 26,000 light-years away, about 4 million suns in mass, a star like S2 completing an orbit in 16 years, reaching relativistic speeds near closest approach, an event horizon radius around 12 million kilometers, smaller than Mercury's orbital neighborhood. So now we hold a terrifying anchor point. This is what a supermassive black hole looks like, next door. But this raises another question, and it's the one that expands our story from our galaxy to the universe itself. If Sagittarius A star is considered relatively small among supermassive black holes, then what kind of objects sit at the centers of the largest galaxies? You're about to see why nearly every large galaxy appears to carry one of these hidden anchors, and why, on the scale of galaxies, black holes stop being curiosities and start becoming architecture. When we look at a galaxy, we see stars, a bright disk, a glowing bulge, spiral arms like frozen storms. But the real ruler of that system often can't be seen at all. At the center of many large galaxies, there appears to be an object so massive that it quietly organizes everything around it. Yet it refuses to shine, refuses to reflect, refuses to confess in the usual ways. You can stare at a Hubble image of a distant galaxy and think you're seeing the whole story. But that's where the universe gets cruel, because the brightest parts are not always the most important parts. Sometimes the true center is a darkness with a weight measured in millions to tens of billions of suns, and once we accept that, a new fear appears. If these giants are everywhere, then black holes aren't rare monsters. They're architecture. Supermassive black holes sit in a different category than the stellar mass black holes born from collapsing stars. These are not a few suns packed tight. These are millions to tens of billions of solar masses, objects so extreme that NASA's own Hubble science team describes them as monster black holes, common in the universe's largest galaxies. And here's the contradiction we have to hold in the same breath. A galaxy can contain hundreds of billions of stars and still be governed, at its core, by a single object that is only a tiny fraction of the galaxy's total mass, yet dominates the deepest central region like a gravitational throne. This is why astronomers took the question personally. Are supermassive black holes a rare accident, or are they a standard part of what it means to build a large galaxy? Hubble's galaxy census and decades of dynamical measurements push the answer in a disturbing direction. In nearly every large galaxy, evidence points to one, but that creates a bigger problem. If we can't see them directly, how do we know they're truly there, and not just a convenient story? Astronomers don't believe in supermassive black holes because they sound dramatic. They accept them because the alternatives collapse under the data. The strongest evidence comes in three kinds of fingerprints: when stars orbit a hidden center with immense speed, when gas swirls as if caught in a deep invisible drain, gravity is speaking. This is the oldest method in the book: measure motion, infer mass. And as reviews like Kormendy and Hose summarize, spatially resolved measurements of stellar and gas dynamics across many galaxies have built a population-level case that supermassive black holes are widespread in galactic centers. Sometimes the black hole's neighborhood does shine, violently. When a supermassive black hole is feeding, matter spirals inward, heats up, and can radiate enough energy to outshine the entire galaxy. That's what quasars and active galactic nuclei are, not the black hole glowing, but the infalling material paying the price of gravity. This is the unnerving part. Hubble's census language is blunt. Supermassive black holes are so common that nearly every large galaxy has one, and their mass scales with the central bulge of stars. So the mystery shifts. Not, do they exist? But why are they so tightly tied to the galaxies that contain them? Here's where the story cracks open. If supermassive black holes were random ornaments, their masses should be all over the place. No pattern, no discipline. But astronomers found correlations that felt almost intentional. One of the most famous is the M-sigma relation. Black hole mass correlates with the typical random speeds of stars in the galaxy's central bulge. This relationship was established in the early 2000s in landmark work by Ferraris and Merritt and by Gebhardt and collaborators, and then refined by later analyses. Another is the relationship between black hole mass and the stellar mass of the bulge, quantified in studies like Herring and Ricks, showing a near-linear connection across a sample of galaxies. And NASA's Hubble team summarizes this in plain terms. The larger the galaxy's central bulge, the larger the black hole tends to be. This is not a perfect rule. There are exceptions, scatter, edge cases. Astronomers argue about details with the seriousness of people who know the universe doesn't hand out clean answers. But the overall pattern is real enough to change how we see galaxies. Galaxies aren't just star cities. They're systems with a hidden central mass that seems to know the scale of the bulge surrounding it. And that raises another question. How can a black hole, occupying a tiny region, be linked so strongly to a structure thousands of light years wide? Imagine this, a crowded playground carousel. The children are the stars in the bulge. The carousel's spinning speed is the random motion astronomers measure, and hidden underneath the platform is a heavy weight bolted to the center. You don't need to see the weight. You only watch how hard it is to spin the ride, how tightly the motion holds. That's the core idea behind these correlations. Astronomers don't measure the black hole with a camera. They measure its influence through the movement of the stars that live in its neighborhood. But then, the universe adds a sharper edge. Even though the black hole's mass is usually a small fraction of the galaxy's total, it can dominate the central gravitational landscape so completely that the inner region becomes its domain. A galaxy is not a solid object. It's a swarm, a cold, rotating ecology of stars, gas, dust, and dark matter. In the outer regions, a single star can drift for millions of years without feeling the details of the core. But in the inner heart, where orbits tighten and time feels faster, gravity becomes personal. A supermassive black hole creates the deepest central potential well. In that inner zone, it can become the primary sculptor of motion, setting the pace for stars and gas that venture too close. And when a supermassive black hole is actively feeding, it can become more than a gravitational anchor. It can become an engine, turning infalling matter into blinding radiation, sometimes launching powerful structures that astronomers observe across the electromagnetic spectrum. Even NASA's Hubble Monster Black Holes feature emphasizes how central dust and gas can fuel these objects. This is where the stakes rise. The galaxy is not just hosting a black hole. The black hole can, at times, rewrite the environment of the galaxy's core. But this creates a deeper mystery, one scientists keep returning to. If supermassive black holes are this common, why does the universe build them in the first place? And why do they track the galaxy bulge so closely? So the picture sharpens. Supermassive black holes are not exotic exceptions tucked into a few strange galaxies. They appear to be a standard feature of large galaxies, supported by Hubble census results, and by decades of dynamical measurements summarized in major reviews. They span a terrifying mass range, millions to tens of billions of suns, and they are not randomly sized. They correlate with the properties of the bulge, with stellar speeds, with bulge mass, relationships established through foundational work and refined ever since. This doesn't make the universe feel safer, it makes it feel more organized, as if every large galaxy is built around a hidden core, a silent mass that rarely shows itself directly, but leaves order in its wake. And that's when the real problem appears. If this is the normal case, then what happens at the extreme end of normal? We came here thinking supermassive black holes were special. What we found is worse. They may be common, the default heart of most large galaxies. But this raises another question that doesn't let go. If galaxies routinely host black holes with millions of solar masses, and some reach into the billions, where does it end? Because astronomers have measured black holes so large that their event horizons could swallow the scale of planetary orbits. Objects like the one imaged in M87 measured at about 6.5 billion solar masses. And beyond that, the universe keeps records of even larger ones. So next, we move from galaxy scale to the outer edge of what's been measured, the largest black holes ever found, and the unsettling question of whether nature has a limit or whether it simply runs out of time. Somewhere in the cold archives of the sky, there is a circle, not a planet, not a star, not even a galaxy, a circle where the universe stops giving things back. And the disturbing part is this: that circle can be so large it could swallow the scale of our solar system like a single grain of dust disappears in a stadium. We say black hole, and our minds reach for a small, violent thing, an invisible puncture in space. But then we meet the largest black holes ever measured, and our intuition fractures. Because with these objects, size stops meaning what we think it means, and our usual comfort, distance, scale, perspective collapses. And here's the question that won't let us go. If nothing can escape a black hole, how can something invisible become this enormous and still remain hidden? Let's ground ourselves. A black hole has a boundary, a point of no return. Cross it and no signal, not even light, can climb back out. Physicists call that boundary the event horizon. Now here's the simple rule that makes everything crack open. For a black hole that isn't spinning, the event horizon grows in direct proportion to mass, and for every sun's worth of mass, that boundary is roughly 3 kilometers farther out. 3 kilometers doesn't sound like much, but that's the trap, because the universe doesn't stop at one sun. It builds black holes with millions, billions, and somehow tens of billions of suns packed into one dark object. And at that point, small and large stop being helpful words. So instead, astronomers do something deeply human. They compare the incomprehensible to what we can picture by using planetary orbits as a ruler. And that's where the story turns monstrous. When astronomers talk about the largest black holes, they're not guessing blindly. They're using real measurements: the motion of stars, the speed of gas, the light from hot matter spiraling inward, and the fingerprints in quasar spectra, methods sharpened over decades of work by observatories and teams around the world. One of the most famous is M87 star, the black hole at the center of the galaxy Messier 87. It's so massive that the Event Horizon Telescope, the Earth-sized radio telescope, was able to reveal its shadow, a ring of light wrapped around darkness. NASA's recent size comparison places M87 star at about 5.4 billion suns, and its shadow is so wide that light would take around 2.5 days to cross it. 2.5 days at light speed, just to cross the silhouette. But then, that isn't the end of the list. It's the warm-up. Because the universe has at least a few black holes that appear to sit in a rarer category, objects so massive we almost hesitate to call them supermassive anymore. One example is the black hole in the galaxy Holm 15A, reported in a 2019 study at around 40 billion suns, with the authors describing it as an uber-massive black hole. 40 billion. Our minds can't hold that cleanly. So we do what astronomers do. We turn mass into size. We ask, how wide is the point of no return? How far does the border spread? And the answer is planetary. Now we arrive at the name that haunts this topic: TON 618. A quasar, meaning we're not looking at a quiet galaxy center. We're looking at a nucleus blazing across the void, powered by matter falling inward and heating to extreme temperatures before it vanishes. And the light from TON 618 takes more than 10 billion years to reach us. We are seeing it as it was when the universe was younger, when galaxies were still assembling their shape. And inside that ancient beacon, NASA describes TON 618 as containing more than 60 billion solar masses, more than 60 billion suns in one object. And then comes the line that turns the stomach just a little. Its shadow is so large that light would take weeks to traverse it. Weeks. Not because light is slow, not because space is thick. Weeks. Because the circle is that big. Imagine you're standing on a school playground with a piece of chalk. You draw a circle on the ground. That circle is the no-return line. Now imagine the circle grows until it covers the whole playground, then the neighborhood, then the entire city. And here's the key. The chalk line isn't the city. It's only the boundary. That's what an event horizon is. Not a giant object you can touch, but a border in space where escape becomes impossible. With TON 618, that border expands until it stops feeling like astronomy and starts feeling like geography. And if you could drift near that boundary, still outside it, you wouldn't see a monster floating in space. You would see normal starlight behind you, and in front of you, a darkness so perfectly defined it would feel like a cut in reality. A circle drawn by gravity itself. Here's the strange part. The largest black holes are not cosmic vacuum cleaners. They don't automatically swallow everything around them. At the distance where planets orbit a star, gravity mostly cares about mass, not whether that mass is a star or a black hole. If our Sun were replaced by a black hole of the same mass, Earth's orbit would remain nearly the same, though the light and heat would be gone and life would end for a different reason. So what makes the giants terrifying isn't that they're sucking harder. It's that their boundaries grow so large that the concept of nearby changes. When the edge itself spans planetary orbit scales, the region where space-time bends violently is not a tiny point. It becomes a realm, a place where the rules of light and time don't merely bend, they begin to betray our expectations. And that brings us to another problem. If black holes can grow this large, why don't we see ones that are 100 times larger? Astronomers don't claim the universe has a single, simple maximum size for black holes, but they do have serious reasons to suspect growth is not unlimited. One limit comes from the fact that black holes grow by feeding, by pulling in gas, dust and stars, and by merging with other black holes. But feeding has consequences. As matter falls in, it heats up and radiates. That radiation pushes back, and at high enough brightness, it can fight the inflow. This is connected to what's often called the Eddington limit, a real, well-established concept in astrophysics. So the black hole's meal can sabotage itself. The brighter the feast, the harder it becomes to keep feeding. And another idea, argued in a 2016 paper by Andrew King, is that accretion disks may become unstable at large scales, meaning there may be a practical ceiling for how massive a black hole can grow through long-term disk feeding, with a characteristic upper range around tens of billions of solar masses. This doesn't make TON 618 less real, it makes it more unsettling. Because if TON 618 is near the upper edge of what physics and cosmic history can build, then it may represent not just a largest known object, but a boundary condition, a place where the universe itself starts to run out of room to scale upward. And that means when you look at TON 618, you're not just looking at something far away, you're looking at something close to the edge of what nature can assemble, before the act of growing collapses under its own consequences. So here's what we've learned, quietly and with discomfort. Black holes can grow until their shadows are measured in days, and even weeks of light travel time. They can become so large that planetary orbits feel like small markings on a ruler. And still, they remain invisible, which raises the deeper question we can't avoid anymore. If the boundary is that enormous, what happens to time as we approach it? Because size is only the beginning. When gravity becomes that extreme, space doesn't just curve. It rearranges the flow of seconds, and in the next movement of our story, we're going to step toward the event horizon, not to cross it, but to watch the universe distort, light bending, clocks disagreeing, reality slowing down, in ways we've already confirmed in real experiments. And this is where everything changes. There's a quiet horror hiding inside black holes. Not the violence, not the darkness, not even the idea that nothing can escape. It's this. Near a black hole, time itself becomes unreliable. Two clocks can start together, identical in every way. And then we separate them by distance and gravity, and they come back disagreeing, not by opinion, by physics. And that creates an uncomfortable question we can't dodge. If time can stretch and slow near the edge of a black hole, what does now even mean there? Because the closer we move toward the event horizon, the more the universe begins to behave like a dream with rules that keep changing. And this isn't poetry. This is Einstein. But here's the real problem. We can't stand at the event horizon and check a stopwatch. We can't send a person to the edge and ask what they saw. So how do we know any of this is real? How do we confirm the warping of time and light without ever touching the place where it happens most? That's where the story cracks open. We've all felt gravity as a force, a weight in our bones, a pressure in our knees, a quiet downward command. But in Einstein's universe, gravity isn't just a pull. It's a change in the shape of space and time, a curve carved into reality by mass. And once we accept that, we inherit a strange consequence. Time is not the same everywhere. Time is not a universal river. It's more like a landscape, where some regions flow fast and some regions flow slow. So when we talk about gravitational time dilation, we're saying something simple, but devastating. A clock deeper in gravity ticks more slowly than a clock far away, and physicists can express that relationship in an equation that's actually speakable. Time near the gravity equals time far away, multiplied by a slowdown factor. That's it. No intimidating symbols. Just a clean idea. Local time is equal to far away time multiply slowdown factor. And the closer we get to the event horizon, the more that slowdown factor shrinks towards zero, which means, from far away, the edge starts to look like a place where time almost stops. But then, that raises a deeper question. If time slows down near the horizon, what happens to light trying to climb out? Light is the universe's messenger. It carries the story of everything: stars, dust, explosions, galaxies. But near a black hole, even light has to fight. As it climbs out of that deep gravitational well, it loses energy. And when light loses energy, it changes color. It shifts toward the red. Astronomers call this gravitational redshift. But we can picture it in a human way. It's like a runner trying to climb a steep hill. Every step costs strength. By the time the runner reaches the top, they're slower, weaker, drained. Light does something similar. It escapes, but it escapes exhausted. And this is where it gets stranger. The closer that light starts to the event horizon, the harder the climb becomes, and the more the light is stretched, until it can slip out of the visible spectrum entirely. So the black hole doesn't just look black because it's dark. It looks black because its light is being dragged into silence. But that's not the whole story, because a black hole doesn't only dim light, it bends it. A black hole is not just a gravitational object. It's a lens so extreme it can distort the sky into a broken ring. Light that would have travelled straight is forced to curve. Some light is bent and escapes. Some light is bent so sharply it loops around once, twice, before finally slipping away. And some light is trapped into orbit. This creates something eerie and beautiful. Near the black hole, space becomes a warped corridor, and light becomes a prisoner pacing the edges. This is not science fiction. teams connected to the Event Horizon Telescope, working across observatories on Earth, have captured images showing the dark shadow region around a black hole, shaped by light bending in extreme gravity. We are literally seeing the outline of a place we cannot see directly. But here's the disturbing part. The closer we get to the event horizon, the more extreme the bending becomes, and the harder it is to tell what is in front, what is behind, and what is even real. So now our mystery sharpens. If light can be bent, delayed, stretched, and dimmed, and time itself can slow down, how can we trust anything we observe near a black hole? Imagine this. We place two perfectly identical watches in a building. One watch goes to the roof, the other goes down into the basement. Nothing dramatic happens. No explosions, no alarms. Just quiet waiting. But here's what gravity does. The basement watch sits slightly deeper in Earth's gravity than the roof watch, and over time, the basement watch falls behind. Not because it's broken, because gravity stole tiny pieces of its time. Now scale that up. Earth's gravity is a gentle slope compared to a black hole. A black hole is a cliff, so if a basement can slow a watch by a whisper, then near a black hole, that whisper becomes a roar, and that leads us to the line where our instincts collapse. Clocks don't disagree because time is weird. Clocks disagree because time is physical. Time can be stretched. Time can be warped. Time can be reshaped by mass. And we don't have to believe that because we've tested it. Scientists hate mysteries that can't be checked, so they check this one. Not near a black hole, but in ways that still test the same physics. Atomic clocks on airplanes have been flown around the Earth and compared to clocks that stayed on the ground. They came back shifted, exactly as relativity predicts. Atomic clocks placed at different altitudes tick at different rates. Higher altitude means slightly weaker gravity and a slightly faster tick. And every single day, something even more practical confirms it. GPS. GPS satellites carry atomic clocks. They live higher up, in weaker gravity, and they move fast. Both effects matter. If engineers didn't correct for relativity, GPS would drift by kilometers, because time itself wouldn't line up between orbit and Earth. So when we talk about time dilation near black holes, we're not starting from a guess. We're starting from a fact. Gravity changes time. We've measured it. We rely on it. But this creates a new problem, because if relativity is real here, then near a black hole it becomes extreme. So what does extreme really mean? Let's keep it clear. If we hover far away from a black hole and watch a clock falling toward the event horizon, we would see it slow down. Its light would redshift. Its signals would stretch. It would appear to approach the edge and never quite cross. But from the clock's own perspective, it ticks normally, second by second, heartbeat by heartbeat. It doesn't feel time slowing inside itself. This is the paradox that makes black holes emotionally heavy. The same event can look frozen from one viewpoint and ordinary from another. Neither is a hallucination. Both are real, within their own frame of reference. And this is why black holes don't just bend light. They bend our certainty. They force us to accept that what happens depends on where we stand in the universe. And now, we're close enough to ask a sharper question. Picture yourself holding a clock, not a metaphorical clock, a real one, a little machine that claims to mark the heartbeat of the cosmos. Now imagine you drift toward a black hole's event horizon, holding that clock in front of your face. You don't feel your seconds stretching. You don't feel your thoughts slowing. But far away, someone watching you would see your clock dim, redden, slow. They would see your signals arrive later and later, until you become a fading ember near a boundary you cannot warn them about, and you realize something cold. The event horizon is not just a place where light can't escape, it's a place where shared reality breaks. But even that isn't the deepest twist, because black holes don't only distort time, they dominate the shape of space itself. The event horizon isn't a physical wall. It's not a solid surface. It's a boundary, a line in space where escape becomes impossible. And what makes it terrifying is how normal it can look locally. A black hole doesn't announce itself with a bright edge. It hides behind its own physics. So how do astronomers deal with this? They measure the black hole indirectly, through what it does to everything around it. They measure how matter heats in an accretion disk. They measure how light is bent. They measure orbits. They measure jets. They measure the timing of signals around extreme gravity. And the story that emerges is consistent. Time dilation is real. Light bending is real. Gravitational redshift is real. Einstein's picture survives every test we've been able to build. And yet, the closer we get to the horizon, the more our descriptions start to strain. Because inside the horizon, we cannot receive information. That means there is a hard limit to what the universe allows us to confirm directly. Not because we lack ambition, but because the cosmos has built a barrier into causality itself, which gives black holes their quiet power. They are objects we can measure with terrifying precision and still never fully witness. And that's where the unease settles in. Even if you never go near a black hole, even if you never see one in your sky, their rules are already inside our world. Your phone's location depends on time dilation being true. Our understanding of stars depends on space-time being real. The shape of galaxies depends on invisible gravity doing visible work. Black holes are not distant monsters. They are proof that the universe is stranger than our instincts and calmer than our fears. But now, one possibility remains. If black holes can bend time and light, what else can they reshape on a much larger scale? Because a black hole is not just a trap, it's an engine. It can launch jets that cut through galaxies. It can heat gas. It can shut down star formation. It can sculpt the growth of entire cosmic cities. So the next question isn't about what black holes destroy. It's about what they quietly build. How can an invisible object become an architect of the universe, shaping galaxies that are trillions of kilometers wide, while remaining hidden behind a shadow? That's where we go next. A galaxy looks like freedom. Hundreds of billions of stars drifting in a wide, cold architecture. Spiral arms like slow hurricanes. A glowing core. A halo you can't see. But buried in the center of many galaxies is something that doesn't look like power at all. A black hole. A region smaller than the distance between planets, carrying a mass measured in millions to billions of suns. And here is the problem. How does something so small reach out and shape something so vast? Not with hands, not with light, with feedback, a word that sounds harmless until we see what it does. Jets, radiation, outflows, shockwaves, cavities in hot gas the size of galaxies. This is where the story stops being about black holes as voids and becomes about black holes as architects. When we study galaxies, we're not studying frozen objects. We're studying ecosystems. Gas cools and falls inward. Stars ignite, supernovae explode, new elements spread, gravity gathers everything again. If a galaxy forms stars too fast, it burns through its fuel and changes its destiny. So astronomers asked a question that sounds almost personal. Why do some massive galaxies stop making stars? Why do they go quiet, while still holding enormous reservoirs of gas around them? A major line of evidence points back to the center. Energy injection from active black holes, AGN feedback, playing a key role in galaxy evolution and quenching, discussed across major observational reviews. But then the universe adds a twist. A black hole doesn't have to touch a galaxy to change it. It only has to change the behavior of gas. And gas is the beginning of everything. Astronomers generally see two dominant channels of black hole influence. When gas falls toward a supermassive black hole, it heats to extreme temperatures and radiates intensely. The galaxy core becomes an engine of light and momentum, sometimes powerful enough to push material outward. This radiative feedback is one of the central themes in observational summaries of AGN feedback. Sometimes, instead of mainly shining, the system launches narrow jets, streams of particles moving close to light speed, punching into surrounding gas. The results aren't subtle. In galaxy clusters, jets carve cavities into hot X-ray gas, literal bubbles blown into intergalactic atmosphere. And here's where everything changes. These aren't rare curiosities. ESA's XMM Newton has found that ultra-fast outflows, winds launched from the vicinity of central black holes, are quite common in active galaxies, appearing in about 40% of the sample they studied. So the question becomes sharper. If black holes are routinely throwing energy outward, what does that energy do to the gas that would otherwise become new stars? Imagine this. We're looking at a huge city in winter. The buildings are the stars. The streets and air are the gas, the raw material that could form more buildings. Now place a powerful heater in the city centre. If it runs too hard, the air becomes turbulent. Nothing settles. Construction slows. If it turns off, cold air sinks and piles up. Construction surges. That's the simplest map of what astronomers mean by self-regulation. A black hole doesn't design a galaxy with intention, but by heating, stirring, or ejecting gas, it can control whether gas settles into star-forming clouds or stays too hot and chaotic to collapse. But then we find something even more unsettling. We can see this regulation written into the structure of galaxy clusters. In some galaxy clusters, the gas between galaxies is a vast hot atmosphere glowing in X-rays, and in that atmosphere, astronomers see scars. In the Perseus cluster, Chandra described cavities or bubbles blown into the cluster gas by jets from a supermassive black hole, disturbances that can generate pressure waves, like sound travelling through a medium. This is not poetic language, it's physics. Jets push, gas moves, waves propagate, energy spreads, and those waves matter because they can deliver heat, helping offset cooling that would otherwise send huge amounts of gas raining down into the centre. Then we look at more extreme cases, and the scale becomes almost violent. NASA's Hubble, Chandra, VLA descriptions of the cluster MS0735 show enormous cavities created by jets ejected at nearly light speed, jets that displaced staggering amounts of gas, and NASA has reported even larger record-breaking black hole outbursts in clusters like Ophiuchus, emphasizing how enormous eruptions can excavate giant cavities in hot gas. So we have a mechanism powerful enough to reshape galaxy cluster atmospheres. But this creates a bigger problem. If black holes can do this to cluster gas, what are they doing inside the galaxies themselves? Astronomers have long suspected that black hole feedback helps explain why massive galaxies often become red and dead, rich in old stars, poor in new ones. The observational challenge is brutal, galaxies are complicated, and feedback can be messy. But the evidence keeps stacking. NASA's Hubble reported cases consistent with star formation being regulated by a fountain cycle tied to a central black hole's jets heating halo gas and controlling how it cools and falls back in to form stars. At the same time, ESA's XMM Newton measurements of ultra-fast outflows suggest that powerful winds from AGN are not rare, and these winds can carry significant energy and momentum into the galaxy environment. And in the high redshift universe, when galaxies were forming stars more intensely, JWST-era studies have reported widespread AGN-driven cold gas outflows, arguing they may be a dominant mechanism for rapid quenching in some systems around redshift 2. Not every galaxy is the same, not every black hole is active at the same time, but the pattern is hard to ignore. Black holes don't just consume, they eject, they heat, they disturb the fuel supply, and fuel supply is fate. You can picture it without needing exotic math. A galaxy is trying to breathe, gas cooling inward, condensing, forming stars. Then the center flares. A jet punches outward. A wind surges. The inner gas is stirred and heated or pushed away. It's like watching fog in a cold valley, ready to settle until a sudden gust tears it apart. The stars we don't form are the history we never get. Here's the strange part. Feedback isn't always a simple off switch. In some environments, black hole jets can compress gas and align it into structures where star formation appears along jet-influenced regions, an idea NASA has highlighted in its black hole fountain framing of a regulating cycle. So the universe doesn't give us a single story like black holes kill stars. It gives us a harsher truth. Black holes control the conditions. They can prevent star formation by heating or ejecting gas. They can influence where star formation happens by reshaping gas flows. Either way, the galaxy is no longer free to evolve on gas alone. It evolves under a central pressure. You can look at a massive galaxy and think it is defined by its stars, but the stars are the record of what the gas was allowed to do. A black hole is like a silent governor inside the engine, rarely visible, sometimes dormant, but capable of changing the entire regime when it activates. And that should feel unsettling, because it means galaxies are not only built bottom-up from starlight and dust, they're shaped top-down by the deepest gravity well in the center, by eruptions that can ripple through gas on scales that dwarf our solar system, and even reach into galaxy cluster space. If we remove supermassive black hole feedback from the story, several puzzles become harder to explain. Why massive galaxies often stop forming stars even when gas exists in their environments. Why we observe enormous cavities and ripples in hot cluster gas linked to central black hole activity. Why fast, energetic outflows are common in active galaxies, as measured by X-ray observatories. This is why astronomers call it feedback, because it closes the loop. The black hole grows by feeding on gas. Then the black hole's output changes the gas. Then the gas changes the galaxy's future, and even the black hole's future. It's a cycle written in light, motion, heat, and absence. We came here thinking black holes were cosmic sinkholes, but the universe had one more twist. They are not only consumers, they are broadcasters, sending energy back into the galaxy, rewriting the conditions for star formation, and sculpting the evolution of the largest structures we know. But that raises the next question, one that moves from slow architecture to sudden violence. What happens when black holes don't just feed and regulate, but collide? Because when two black holes merge, the universe doesn't just change locally. It rings, sending gravitational waves across space-time itself. And that's where we go next. For most of human history, we've been trapped inside one sense. We watch the cosmos, we collect light, we translate distant glow into meaning. But black hole mergers don't announce themselves with light. They announce themselves by moving space-time itself. A passing gravitational wave doesn't just arrive like information. It arrives like a physical presence, stretching and squeezing reality in a rhythm too subtle for our bodies to feel, but real enough for our instruments to measure. And in 2015, that rhythm finally reached us. Not as a picture, as a tremor. A signal so small it should have been lost forever. Except it wasn't. In 1916, Einstein's general relativity didn't just change gravity. It predicted something almost unsettling, that accelerating massive objects would send ripples through space-time, waves that travel outward, carrying the story of what happened. For decades, gravitational waves lived in a strange place, accepted by theory, hunted by engineers, doubted by intuition. Because here's the problem. If space-time itself is what's waving, what could ever measure it? We can't stand outside the universe and watch it flex. So we built a ruler so precise it borders on the impossible. LIGO is not a telescope. It's a pair of giant interferometers, one in Livingston, Louisiana, one in Hanford, Washington, built to notice a difference in length so tiny it feels absurd. Two long arms, laser light, mirrors hanging in extreme isolation. The idea is simple to say and brutal to achieve. If a gravitational wave passes through Earth, it slightly stretches one arm while squeezing the other, then swaps, and that shifting pattern imprints itself into the laser's interference, a disturbance not in the air, not in the ground, in the geometry we live inside. And then, on September 14, 2015, both detectors felt the same whisper. The signal arrived at both LIGO sites, separated by thousands of kilometers, almost the same moment. It lasted only a fraction of a second in the sensitive band, but inside that fraction was a full narrative, a low, steady rhythm, then faster, then a sudden cut-off. Scientists call this pattern a chirp, not because it's cute, because it's what happens when two massive objects spiral inward, each orbit shorter than the last, each moment more violent than the one before, until the merger becomes a single catastrophic event. This was the first time we didn't just infer gravitational waves, we heard the universe behave exactly as Einstein said it should. Imagine this. We're watching two ice skaters holding hands, spinning. At first, their circle is wide, the spin is slower, then they pull closer, the circle shrinks, the spin speeds up. Nothing magical happened, the same motion simply tightened. That is the cleanest human picture of a black hole in spiral. Far apart, the orbit is slower. Close together, the orbit accelerates. And right before impact, the spin-up becomes a scream written into space-time. That rising rhythm is the chirp, and it tells us something crucial. Not just that the merger happened, but how massive it was. Gravitational waves carry information the way a voice carries identity, not by describing itself, by its shape. From the waveform alone, its rising frequency, its amplitude, the way it ends, astronomers can infer key properties of the system using models of black hole mergers built directly from general relativity. For the first historic event, GW 150914, LIGO scientists estimated two black holes of about 29 and 36 times the mass of the Sun, merging into a single remnant. And here's where scale becomes terrifying. In that merger, about 3 suns worth of mass energy was carried away as gravitational waves, in a fraction of a second. The peak power output was described by LIGO as roughly 50 times the power of the whole visible universe, momentarily. This is not a metaphor. It's one of the most intense releases of energy we've ever measured, but it's invisible to our eyes, because the energy didn't leave as light. It left as a rearrangement of space-time itself. You can sit in a quiet room today and realize something cold. That signal began its journey roughly 1.3 billion years ago, before complex life had its current shape on Earth, before our continents looked familiar, before any human story. Two black holes merged in deep space, and the universe kept the receipt, a ripple traveling at light speed, crossing intergalactic darkness, passing through countless stars until it finally brushed Earth, just enough for our machines to notice. And that raises another question. If the signal is so tiny when it arrives, how can we trust what it says? Scientists hate mysteries, but they fear false positives even more. So the detection wasn't accepted because it was dramatic. It was accepted because it was consistent, across detectors, across methods, across theory. The waveform matched the predictions of general relativity for a binary black hole merger, through inspiral, merger, and the final ring down, when the newly formed black hole settles into a stable state. And the collaboration didn't stop at "it looks right." They performed explicit tests, checking whether the early part and late part of the signal agree on the final black hole's properties, and whether the post-merger oscillation matches the expected behavior of a remnant black hole in relativity. This was the payoff. The most extreme high-speed, strong-gravity dance we've ever measured still obeyed Einstein. No cracks, no obvious violation, just an older truth surviving a harsher trial. General relativity had already passed many tests: light bending near the Sun, time dilation near Earth, and precise orbital effects. But black hole mergers push gravity into a regime that is violently nonlinear, where the field itself becomes dynamic. GW 150914 offered an unprecedented chance to test relativity where it becomes most uncomfortable, near the brink of a horizon at high velocities, with space-time actively shaking. The result, within uncertainty. The signal was consistent with general relativity's predictions in the strong field regime. That's why this detection was more than "we found something." It was, the universe still follows the rules even at its most violent edge. You might think this chapter is about a collision, but it's really about scale becoming measurable, because gravitational waves don't give us a photograph, they give us a calibration. They tell us how heavy the objects were, how fast the spiral tightened, how much energy was released, and how far away the event occurred, because distance is written into how faint the wave arrives. It's the universe speaking in a language of compression and timing, and we finally learned to listen. So now we've crossed a threshold. We've watched black holes merge. We've seen energy escape without light. We've heard space-time ring like a struck bell. But this creates a new problem, because once we can measure black holes through their waves, we're forced to confront a harder comparison. How do black holes stack up against stars, galaxies, galaxy clusters? What does dominant really mean? Mass, density, influence, or volume? And why do so many people still imagine black holes as cosmic vacuum cleaners? That's where the story goes next. When we say black hole, most of us picture the same thing. A cosmic vacuum, a mouth in space, a predator that can swallow a galaxy like it's nothing. But that image is wrong, and the truth is more unsettling because it's quieter. A black hole is not defined by how much it chases. It's defined by how much it concentrates. It can hold the mass of millions of suns inside a region, not much larger than the space our planets move through, yet still be a tiny dot compared to the galaxy around it. So here's the central mystery we have to face. If black holes are so dense they can trap light, why isn't the universe already gone? In our minds, bigger usually means dominant. But cosmic scale doesn't follow human instinct. A black hole is extreme mass concentration. A galaxy is extreme mass distribution. A galaxy cluster is extreme mass total, the largest gravitationally bound structures we know. So when we compare black holes to everything else, we can't just ask, how heavy is it? We have to ask, how spread out is it? How close do we have to get before it matters? What does it control, and what merely orbits it? And this is where everything changes. Because gravity doesn't care about drama, it cares about distance. Here's the strange part. From far enough away, a black hole's gravity behaves like the gravity of any object with the same mass. NASA says it plainly. Black holes don't suck in other matter like vacuum cleaners, and at large distances, their gravity is like any other object of the same mass. So, if a star like our Sun were replaced, instantly, by a black hole of the same mass, Earth would keep orbiting in essentially the same path. NASA's own educational material states this directly. The difference isn't more gravity everywhere. The difference is what happens near the center. A normal star has a surface. You can orbit it, fly past it, even skim it, if you could survive the heat. A black hole has a boundary, an event horizon, where escape stops being possible. NASA defines it as a boundary where not even light can escape. So black holes don't win by reaching farther. They win by making the inner region final. Imagine this. We fill a football stadium with fog. That fog is a galaxy's mass, spread out, wide, diluted across enormous space. Now imagine we take the same amount of material and crush it into a single marble. That marble is not more material. It's the same material, just concentrated. That's the difference we're dealing with. Galaxies are stadiums of mass. Black holes are marbles of mass. And marbles don't dominate the stadium by being large. They dominate by being dense enough to change what happens when you get close. Now we go up a level. Our Milky Way's total mass is about 1.5 trillion times the Sun's mass, according to NASA's analysis using Hubble and Gaia data. In that same galaxy, the central black hole, Sagittarius A star, is about 4 million suns. That means the black hole is not most of the galaxy, not even close. So why do we treat it like the galaxy's king? Because the black hole doesn't need to outweigh the galaxy to shape it. It only needs to control the inner traffic, how gas falls inward, how energy gets released, how matter heats, spins, and sometimes erupts outward. A supermassive black hole is small compared to the galaxy's size, but it can sit at the deepest point of the gravitational landscape. A deep valley doesn't cover the whole continent, but rivers still find it. This is the comparison most people miss. A galaxy dominates by volume. A black hole dominates by conditions. In most of a galaxy, stars orbit peacefully for billions of years. Only near the very center do black holes become unavoidable, where tides grow extreme, where orbits become dangerous, where matter can be heated to brilliance before it disappears. So we have two kinds of dominance. Spatial dominance, how much space an object occupies, how far it spreads. Concentration dominance, how much mass is packed into a small region, and how extreme the physics becomes nearby. Black holes are the champions of concentration. Galaxies are the champions of spread. And then, galaxy clusters arrive. A galaxy cluster can contain hundreds to thousands of galaxies, bound together in a vast gravitational web. NASA describes galaxy clusters as the most massive gravitationally bound objects in the universe, reaching up to 1,000 trillion suns in mass. That is a number so large it feels like it should crush meaning itself. And yet, here's the uncomfortable truth. Even in a galaxy cluster, black holes still matter. Not because they outweigh the cluster, but because black holes can inject energy into their surroundings, carving cavities in hot gas, launching jets, regulating cooling, shaping the environment inside the cluster over cosmic time. We've already seen that architecture in the last chapter's logic. So scale stacks on scale, clusters dominate by total mass galaxies, dominate by structure and history, black holes dominate by extremity and consequence. Each one rules a different category of reality. Now we face the most common misconception directly. Black holes are not cosmic vacuum cleaners. NASA says so plainly. So why does the myth survive? Because our brains confuse two things. Strong gravity nearby with endless reach everywhere. A black hole's gravity doesn't extend farther than any other object's gravity of the same mass. What's different is the no-return boundary, and the violent gradients close in. To get swallowed, matter usually has to lose energy and angular momentum, its sideways motion, so it can fall inward instead of orbiting. Most things in space have too much sideways motion. They keep circling, like planets around the sun. That's why the sky is not collapsing into the center. Not because black holes are gentle, but because orbital motion is stubborn. You can feel how the myth grips the mind. We imagine a black hole like a drain, but space doesn't behave like a bathtub. There's no friction to spiral everything inward automatically. There's no universal flow pushing matter into the dark. Instead, we get orbits. Endless, quiet, stable paths until something disturbs them. And that is more chilling than the myth, because it means black holes don't need to hunt. They wait inside the math. If Hollywood overstates the sucking, it often understates the real dangers. Near a black hole, the hazards are physical and precise. Tidal forces can stretch and compress objects, because gravity changes rapidly with distance near the center. Accretion disks can radiate intensely as matter heats up before crossing the horizon. Jets and outflows can affect regions far beyond the event horizon, not because matter escapes the black hole, but because energy is released in the infalling process. NASA's descriptions emphasize that black holes are not holes in space, but extreme concentrations of matter with an event horizon boundary. So the honest story is this: a black hole is not a vacuum cleaner. It is a trap with a narrow mouth and an environment around it that can be violently bright. Here's where the story cracks open again. Black holes are tiny compared to galaxies, yet they've become the most emotionally dominant objects in astronomy. Why? Because our minds respond more strongly to boundaries than to volumes. A galaxy is vast, but it feels navigable. A black hole has a line you don't cross, and that boundary turns a simple comparison, mass versus mass, into something philosophical. What is bigger? What is stronger? What is more important? A galaxy holds more mass overall than its central black hole. A cluster holds vastly more mass than a galaxy. But a black hole holds the most extreme rule, and rules change everything. You and I live in a universe where most of reality is stable. Most stars orbit without falling. Most galaxies rotate without collapsing inward. Most of space is calm. And yet, tucked inside that calm are small regions where the universe stops negotiating, where even light can't bargain its way out. That contrast is the true scale, not just how large something is, but how absolute it becomes when we get close. So when we compare black holes to everything else, we can hold the truth in one clean frame. Stars dominate by making light and building elements. Galaxies dominate by structure, vast ecosystems of stars, gas, and time. Galaxy clusters dominate by total mass and gravitational architecture on the largest bound scales. Black holes dominate by concentration and boundaries, small in size, extreme in consequence. And the biggest misconception, they suck everything, dies under one simple fact. From far away, they behave like any other mass. We've corrected the myth. We've placed black holes in their true category, not cosmic vacuums, but cosmic limits. And now we're left with the final discomfort. If the universe's most powerful objects can be invisible, if the most important boundaries can be untouchable, and if we can still measure them with light, motion, and waves, what does it mean about us? About the kind of minds we have that can't visit these places, can't survive them, can't see them directly, and still reach them with understanding. That quiet meaning is where our journey ends next. There's a strange confession hidden inside modern astronomy. The most powerful objects we know are the ones we cannot see. Not with our eyes, not with our cameras, not in the way our instincts demand. Black holes don't shine, they don't glow, they don't announce themselves like stars do. And yet, they rearrange galaxies, they twist light, they warp time, they set entire regions of space into motion, like a silent engine buried under the floorboards of the cosmos. Here's the quiet discomfort. If the universe can hide its greatest forces in total darkness, what else are we missing? Just because our senses weren't built for the true scale of reality. We tend to think knowledge means contact, touch it, see it, stand next to it. But astronomy was forced to grow up early. We can't walk to the sun. We can't lean over the edge of a black hole. We can't bring a galaxy into a lab. So we learned a harder kind of knowing. We learned to measure. That's what scientists at places like NASA, ESA, and observatories across Earth have been doing for generations. Not claiming certainty where it doesn't belong, but building a map from consequences. Because the universe is honest. It always shows its effects, even when it refuses to show its face. And black holes are the purest example of that bargain. They are limits of human access, but not limits of human understanding. Not unless we give up. Here's where the story cracks open. Black holes are often described like holes, but that word is a trap. A black hole is not emptiness. It is mass, so concentrated that the usual paths out of that region of space are sealed. And once we accept that, the next realization hits harder. Black holes reshape everything around them without ever needing to be seen. Gas spirals in, heating until it blazes in X-rays. Stars orbit something they cannot touch. Jets, some of them stretching thousands of light years, can erupt from the centers of galaxies, marking where a supermassive black hole is feeding. Astronomers don't guess this from poetry. They read it in data, in the motion of stars, in the glow of accretion disks, in radio waves and X-rays, in the gravitational waves detected by LIGO and Virgo when black holes collide. But that creates a deeper mystery. If black holes can dominate from invisibility, what does that say about the universe we think we live in, where only the visible feels real? Imagine this. We place a smooth wooden table in front of us. On top of it, we scatter small metal paper clips. They sit still, quiet, ordinary. Now, without telling anyone, we slide a strong magnet under the table. Nothing on the surface looks different at first, but then the paper clips begin to move. They twitch, they roll, they gather into patterns, pulled by something hidden. We can't see the magnet, but we can't deny its presence either. That is how black holes announce themselves, not by appearance, by behavior, by what they force matter and light to do, whether we like it or not. This is the part that still feels impossible, even when it's true. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, M87 Star, in a galaxy about 55 million light-years away. In 2022, they followed with an image of the shadow around Sagittarius A star, the black hole at the center of our own Milky Way. Think about what that means. We did not photograph a thing the way we photograph a mountain. We photographed a boundary, light bent, captured and rearranged by gravity so extreme that space becomes a kind of lens and a kind of trap at the same time. It wasn't a victory over mystery. It was something more unsettling, a reminder that even when we see a black hole, we are still seeing its effects, not a surface. And that's not a weakness of our instruments. That's a fundamental truth about black holes. Now we arrive at the emotional core. Black holes are not frightening because they eat. They are frightening because they reveal an uncomfortable hierarchy. Reality does not care what we can touch. Reality does not care what we can picture. The universe runs on forces and scales that do not ask for our permission. And yet, we've built ways to understand it anyway. We've tracked stars orbiting Sagittarius A star for decades, measuring a mass of about 4 million suns without ever seeing the object itself. We've measured supermassive black holes in distant galaxies by how fast gas and stars move near their centers. We've heard black holes merge through gravitational waves, ripples in space-time itself, arriving at Earth after traveling for hundreds of millions, sometimes billions of years. That should be impossible for a species that once measured distance by footsteps. But this is why it matters. Black holes are not the failure of human knowing. They are proof of what human knowing can become. If you ever felt small while looking at a night sky, that feeling is honest, but it's incomplete, because the sky doesn't just make us small, it also reveals what we are capable of. We are made of the same physics as everything out there, and somehow, we've learned to read the universe's handwriting, even when it writes in darkness. We should say this clearly. We will not visit a black hole, not in any practical human sense. They are too far, too hostile, too extreme. And yet, we can still measure them. We can estimate their masses. We can map their influence. We can predict the shapes of orbits around them. We can test Einstein's general relativity in regimes that no laboratory on Earth can reproduce. This is not fantasy. This is what science does when it refuses to surrender to distance. And the strange beauty is this. Measuring something doesn't require owning it. Understanding something doesn't require conquering it. In fact, black holes teach us the opposite lesson, that true knowledge is often humble. It listens, it watches, it accepts limits, and works precisely within them. Stephen Hawking once helped shape how we think about black holes and information. Einstein showed us gravity isn't just a pull, it's the geometry of space-time itself. And long before their names became cultural icons, the deeper truth was already there. The universe is not built to be intuitive. So when our intuition breaks, that isn't the universe mocking us. It's the universe inviting us to upgrade our understanding. black holes mark the edge of where our everyday thinking collapses, but they also mark something else, the edge of where our most careful measurements begin. And that's why black holes are not just cosmic monsters. They are mirrors. They reflect our limitations back at us, and then they show us how far we can go anyway. And if you came here looking for fear, what we find is something quieter, a different kind of power. Not the power to dominate the universe, but the power to understand it without touching it, to stand on one small world orbiting one ordinary star inside one spiral galaxy, and still measure the invisible architects at its core. That's not arrogance, that's reverence with tools. So what is the quiet meaning of immense scale? It's this. Black holes show us that the universe's deepest truths aren't always visible. They aren't always approachable. They aren't always comforting, but they are measurable. And the act of measuring, carefully, honestly, without pretending we are more than we are, is one of the most human things we've ever done. Scale doesn't have to frighten us, not when we approach it with the right posture, because understanding scale does something subtle to the mind. It shrinks our ego, but expands our sense of belonging. It reminds us that we are not outside the universe looking in. We are the universe, becoming aware of itself, one measurement at a time. But that's not the whole story, because once we accept that black holes can be measured without being seen, a bigger question replaces the old one. If we can map darkness this well, what happens when we push farther, when we build sharper telescopes, when we listen longer for gravitational waves, when we measure the universe with instruments we haven't invented yet? We are not finished. We are only learning how to read a cosmos that speaks in silence. And somewhere in that silence, the universe still has secrets that will not be visible until we learn how to measure them.